Welcome to the 13th session for the Flipped Classroom for AP Calculus. Today we're going to talk about the derivative as a rate of change. Definition: the instantaneous rate of change of a function at some value of x can be defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. You may recognize this as the formal definition of the derivative. So if we want to know the instantaneous rate of change of s of t equals negative 4.9 t squared when t equals 3, we could use this definition to find the derivative, which would be negative 9.8 times t. The rate of change, by sticking 3 in for t, would be negative 29.4. What we just calculated here is the instantaneous velocity of an object dropped from rest at time t equals 3 seconds. Remember that our definition of velocity is the rate of change of an object's displacement. In other words, how fast is your displacement changing? The negative sign in this case just means the object is moving towards Earth. If it was moving away from Earth, it would be a positive sign. Instantaneous velocity is the derivative of the position function s of t. There is a difference between speed and velocity. In everyday terms, people use these terms, interchange these terms. But in physics, speed is velocity without directions. In other words, speed of a falling object would just be 29.4 meters per second, while its velocity would be 29.4 meters per second towards Earth, or a negative 29.4 meters per second. You can calculate speed using an object's distance, while velocity is calculated using the object's displacement. A simple way to change velocity into speed for negative and positive is just to take the absolute value of velocity, and that will give you its speed. Acceleration and jerk. Two other ways to describe an object's motion would be the idea of acceleration, in this case instantaneous acceleration, which is the rate of change of velocity, or in calculus, it would be the derivative of the velocity function, or the second derivative of the position function. You might say, what? In other words, we want to find the rate of change of velocity. The derivative is the instantaneous rate of change. So let's just take the derivative of the velocity. Or that would be the second derivative of the position function, because velocity itself is already a derivative. Okay? Jerk, is the instantaneous rate of change of acceleration. So it would be the derivative of the acceleration function. Okay, usually jerk is when you don't have a uniform acceleration. Difference between distance and displacement. This is fairly simple. If you run around the track, your distance is 400 meters, but your displacement is 0, because you basically have ended up where you started. Okay, distance is how far you went. Displacement is how far you are from where you started. Okay? How can we use this? Let's say the position function is negative 16t squared plus 160t for a moving object. The object's distance can be found by evaluating the s of t at a specific value of t. To find displacement, you need to look at a graph of the function. Why? Because the object may be moving up and down, in other words, farther away from its starting position, and then turning and getting closer to its starting position. Okay, here's a graph of a simple function. Okay, as you can see, this function is a parabola, and the arrow shows at one point the distance is approximately 280, because it has gone from negative 160 to 0 all the way back down to negative 120. That means in terms of total distance, this object has moved 280, but its displacement, okay, how far it is from where it started, if you assume it started at negative 160, is only 40, because it now has ended up at where the arrow is at negative 120. So displacement would be 40 in the positive direction. Height, velocity, and acceleration of this function. If the original function represents the motion of an object thrown into the air, again, s of t equals negative 16t squared plus 160t, we can answer some questions. For example, what is the object's maximum height? Or what is the object's velocity and speed when it is 256 feet above the ground? This shows the usefulness of calculus. This is a direct application to a real-world situation. Next slide will show us how to do this. Finding maximum height. Step 1. Take the derivative of the position function. Remember, the position function is negative 16t squared plus 160t. The first derivative would be negative 32t plus 160. When this object hits maximum height, the derivative will equal 0 as it represents velocity. Excuse me. An object, when you throw it up in the air, does actually stop for a minute in the vertical direction. So we would say its velocity at maximum height would be 0. So let's set the derivative, s prime of t, equal to 0 and solve for t. This yields a value of 5 seconds. What does this mean? 5 seconds after this object is thrown, launched, or shot into the air, it will reach its maximum height. In this case, I believe it could be a rock or anything. Plug this value of t into the original equation, the position equation, to find the maximum height. So s of 5 yields a height of 400 feet. Therefore, this object achieved a maximum height of 400 feet. Pretty cool. To find the speed and velocity at 256 feet, all we do is we take our position equation, set it equal to 256, because that's how far it will have gone, and solve for t. In order to do this, you need to rearrange this equation, set it equal to 0, and then find the roots of the equation by using your old friend, the quadratic equation. Okay? Once you do this, you find that this equation, when set equal to 0, will equal 0 when t has a value of 2 or 8 seconds. Okay, take those values. Keep in mind, this tells me that this object is at 256 feet from the ground when t is 2 seconds or 8 seconds. That makes sense because the object goes up and the object comes down. So there will be 2 times where this is true. Take 2 and plug it into our velocity equation, s prime of 2, which remember equals negative 32t plus 160, yields a velocity at 2 seconds of 96 feet per second, and at 8 seconds, negative 96 feet per second, which makes sense because it's coming towards Earth at 8 seconds. The speed at these 2 times would just be the absolute value of velocity, or 96 feet per second. Again, awesome. There are other applications, such as economics applications, that we will talk about in class and show how to do those, okay? Today, what I want you to consider are the practice problems on page 169 to 172, numbers 1 through 16, and numbers 20 through 26. See you later.